So I know it's really tough for you to come this morning. So I will try to make today simpler. So let's go through the slides and then we will see what we do after the slide. From yesterday, we said the stress could be dynamic. So there's an average value and also an amplitude. So the worst case would be the mean value plus the amplitude. That's why we want the mean and the amplitude to be the summation of them smaller than the yield strength. That's the easiest concept. However, there's a different model. There's someone called Goodman. So there's a good person in design of mechanical components. He's Goodman. Okay. So this person, Goodman, introduced a new idea about dynamic loading. And there are some reasons. So I think the easiest way to understand the model is to use this figure instead of observing the equation. The equation doesn't make sense. It's hard to understand. But if you look at the drawing right here, it's easier to understand. So what happened was, in this drawing, we already draw this design boundary in this two axis coordinate. The horizontal coordinate is the mean value. The vertical one is the amplitude. So earlier we have this yield line. We have limits at the yielding point and also yielding point here. So we draw a straight line. We don't want any design on the upper right corner of this red line. Now, in the idea of fatigue, we know the strength of the material will reduce when we have cycles of loads. When the cycles of loads increases, the strength decreases. So for metal, there's like a saturation point, like a average, like a minimum point, minimum strength. That's so-called the endurance limit, right? So SE represents endurance limit, as what we mentioned in the previous slide. We said with numbers of cycles, the strength reduces, drops up to a certain point. Okay? Sorry. So the idea is that the amplitude of the stress is representing the dynamic part of the stress, not the mean one. Because the mean one, the mean stress, if we are applying exact same stress over the time, it's just that we have cycles. If that stress is always looking like that with a certain mean and certain amplitude, then the mean doesn't change with time. So what is making the material strength reduces is actually the amplitude. So Goodman believes you want to set up the limit at the endurance limit, not the yield point. So he reduced the upper limit to this area. Okay, there's a drop. So whenever you have a design boundary reducing, that means you want this to be more conservative. So Goodman apply a design limit at the endurance limit with a more conservative mindset. Okay? However, since the amplitude part is responsible for the fatigue. How about the mean value part? So if you take a look at dynamic load, this is time, and this is like the varying stress, and this is the mean, okay? So the idea is that there's a tons of times where your stress is actually lower than the mean. Okay, if you only focus on the mean stress, okay? And then you take a look at how the dynamic stress is being applied to the material. In fact, because of the fluctuation, many times the stress is actually lower than the mean. So Goodman believes you can actually enlarge your mean value a little bit. Okay, so that's why he chose the ultimate tensile strength as the upper limit. So he defined a new boundary, design boundary for fatigue. Okay? And the blue line, once you have this boundary, it's easier to have a math function. So this is actually how you formulate that blue line. Okay, so the mean value divided by its upper limit plus the amplitude divided by its upper limit must be smaller than 1. That would be the blue line. So Goodman chose to be more conservative on the amplitude part and used the endurance limit as the upper bound, but he believes for the mean value you can actually have a higher upper bound, so he chose to use the ultimate tensile strength. That's the model. So once you have this equation, if you want to apply safety factor, all you need to do is to have n on the right-hand side of your equation. Then you will get this dashed line right here. Okay? Now, there's another person, Soderberg. Soderberg decided to be more conservative. He agrees with Goodman that we should have a more conservative upper bound at the endurance limit. However, he doesn't believe for the mean value you can actually set up a bound at the optimal tensile strength. He believes we should keep the same upper bound at the yielding strength. So Soderberg is the most conservative model, in fact, in fatigue design for fatigue. So basically, we're looking for this green line. How do you get the green line? Basically, the mean value divided by the upper limit, which is the yielding point, plus the amplitude divided by the endurance limit must be smaller than 1. And similarly, if you apply safety factor on the right-hand side of the equation, you get the dashed line. Okay, as you can see, when you are more conservative, your design space becomes smaller. So if you Google and look for some other models, there's a modified Goodman. So what does modified Goodman look like? Modified Goodman is a combination of the red line and the blue line. So modified Goodman chose to use the union area underneath the blue and the red. So you are conservative on the dynamic part, the amplitude part, and also you can be a little bit more conservative on the mean value part. However, you do have a extra design space right here, like a triangular area that allows you to have more designs. And this area is less conservative than Soderbergh. So if you Google modify Goodman, you'll see it. Trying to find here. This person's notes mention this green area is the modified group. Okay? So now in fact, if you keep on searching for other models, I think this one is a good example. Actually, this is already this is a figure from the same book, Soderbergh. Over here, there's a elliptic line, and also some line called Gerber. So they are like a curved model located. Has a intersection with same upper limit, but they don't believe you can only have straight line for your design limit. So there are actually some other models that believes you can have more design space on the upper right area. So it allows you to have greater mean value and also greater amplitude. But like I said, they're models. Okay? How did they come up with this? Usually they have experiments and they realize, okay, it kind of makes sense. So let me see if they have experiment data. So here, usually when researcher tries to build a model like this, they don't just one day realize, this must be making sense. They actually have experiments. And they observe how the experimental data behaves and realize, okay, the linear model probably was too conservative, even though the mathematical equation looks simpler, but they believe, okay, there are actually some design space at the upper right corner, close to the straight line. Sorry. So usually what happened was researchers did a bunch of experiments. They decided, in reality, you actually can have a greater design space. So I think this is still a research area. So there must be a lot of research papers, like this one. Definitely, this is like a research paper. There are people studying how those curves should be designed. I'm not in this field, so I personally don't work on those models, but I know there are researchers working on these. But in the course, we just learn the most fundamental model. Okay, these three are the most famous linear models. we first start with yielding line, and then because of fatigue, we believe we should be more conservative on the amplitude part. And Goodman and Soderberg have different ideas about the upper limit for the mean stress part. Okay. Now, since we have those, we can put them all together and try to compare them. I always recommend students not to memorize this because they look so alike with each other, and you just cannot remember this too easily. So I think the easiest way to memorize all these three is to follow the diagram. Okay. So for the horizontal axis, you have upper limit at the yielding point and the ultimate tensile strength. For the vertical one, there's a endurance limit and the yielding strength. So usually for metal, ultimate tensile strength is greater than the yielding point, and yielding point usually is greater than the endurance limit. Endurance limit could be as low as a half of the ultimate tensile strength. Okay, so usually the yielding strength and the ultimate tensile strength are not too far away. Because think about how metal breaks. This is stress, this is, which part? This is stress, here is strain. So in the linear part, this is your Young's modulus, right? So here's your yielding strength. After yielding strength, it starts to nonlinearly deform, and then sometimes it breaks right here. So here is your ultimate tensile strength. Usually this ultimate tensile strength is not too far away from the yielding strength. But the strength of the material could drop down to as low as, for example, maybe here. The endurance limit could be as low as a half of the ultimate tensile strength. Okay, so the endurance limit could be, usually is lower than yielding point. Okay, so that's why the design equation, the design boundary looks like this. They believe due to fatigue and after a certain amount of cycles, the strength drops to a lower level. So we should use this lower value as our design upper bound. Okay? So once we have those, the rest is just to try those models in different problems. This is a general plane stress and plane strain problem where we do have stress along two x and y directions, and also we have shear. So in this general problem, the Mohr circle looks like this. So here's an issue, and here's where things become a little bit confusing. For the fatigue model, you realize everything's about the stress, normal stress. There's nothing about shear stress. These equations has no shear stress. But how do we apply the fatigue model to a general problem like this where we have shear stress? So there is a good way to introduce the effect of shearing stress in those fatigue models. That way is to use the von Mises stress. Because von Mises stress is like an equivalent stress without direction. It has the unit, it has value, it has dimension, but it has no direction. It's an equivalent stress that represents the stress stresses in all directions. Okay? So, in fact, when we use the fatigue model for the mean value of the stress or the amplitude of the stress, we actually would like to use von Mises stress for those. So we can, in any problem that comes with shear stress, we still can consider those inside the general equation. Okay, so the von Mises stress, the general equation looks like this. This was derived yesterday when we talked about the maximum distortion energy model. And this is the a shorter expression when the stress along the z direction equals to 0. Okay. Now, here's how we plug in everything. So what happened is, we now would like to choose von Mises stress for each fatigue model, and we will separate the von Mises stress into two parts, the mean value part and the amplitude part. Okay? There are still stresses, and so if we formulate the general equation for plane stress and plane strain problems, the von Mises stress equation looks exactly the same as how we derived earlier. However, we now separate them into two parts. Here's the mean value part and the amplitude part. Okay? So an easier way to compute this is to just plug in all the mean values along x and y over here, and plug in the amplitude along x and y over here. Okay? Now, how do we get the mean value of stress in x and the mean value of the stress in y? We actually check the Mohr circle, and we realize the mean value of, this is like a S1, this is like S2. So the first principal stress and the second one. So we can compute those by the general equation, where you try to compute S1, right? You use the expression of sigma A, sigma B, and tau A. Okay, so these are how you can compute the mean of sigma, the first principal stress, and the amplitude of the first principal stress, mean of the second one, and amplitude of the second one. So this is like a very general case where we have, this one is a simpler one. Because over here we have sigma B, but for shaft problems, we don't have sigma B. So this is actually a little simpler than this problem, okay? But even if we have the problem in the previous slide, same thing, you still can derive in this way. So you just need to compute the mean of each principal stress by the mean of sigma and the mean of tau, and also compute the amplitude of principal stress. You use the amplitude of the sigma and amplitude of tau. Okay? Now, to make everything even more complex, you can, let me show you how things could be even more, become even messier. So let's say we are using Goodman. So S von Mises mean over ultimate tensile strength plus S von Mises amplitude over yielding strength must be smaller than 1 over n, where the mean of the von Mises stress can be computed by S1 mean square plus S2 mean square minus S1 mean times S2 mean, right? Where S1 mean equals to, if we are dealing with a shaft problem, then this is sigma mean over 2 plus sigma mean square over 4 plus tau mean square. Okay, if we have a shaft problem with bending and torsion. Also, another where, how about sigma mean and tau mean? Basically can be computed by 32 moment mean over pi d cube is equals to 16 torque mean over pi d cube. So in fact, what you usually know is the moment and torque. So here comes the situation. What if you have a shaft that is always spinning? Then the load applied to the shaft is always changing with time, varies with time. So if the stress varies with time, or if the moment and torque varies with time, here's where you want to take a look and see if that load condition is gonna cause a fatigue problem. So there are many situations that we will talk about later. We do have problems where you have a mean value of the moment, mean value of the torque. Sometimes you have amplitude, and amplitude for torque. So you plug back in, this equation actually becomes super long, super complex, okay? Imagine this guy comes to here. Imagine this guy came from here. Imagine all this plug in here. So this is actually very long. I never ask my student try to memorize this, but in fact, when I probably 7 or 8 years ago, when I first taught this course, the other professor asked the students to memorize everything. They want the students to memorize the final expression. I don't think it's necessary. Anyway, now there's an important effect, so-called stress concentration. Stress concentration actually plays an important role in mechanical design, especially when your geometry is not very simple. And it not only plays a role in fatigue, it actually also plays a role for static loading. But it is until now we start to talk about the effect of stress concentration. So what is stress concentration? There's something called stress concentration factor. This usually we use a value K. So K equals to in a mechanical part, let's say it's carrying some kind of load, and if we don't talk about stress concentration, there's you can use mechanics of material to compute the stress value that we usually know. So we call those values the reference stress. However, in reality, maybe due to the geometry, stress actually concentrates at some corners, some locations. Like if there's a hole, there's a notch, there's like a fillet or a corner, stress concentrates more at those positions. So the stress value at those corners usually cannot be computed by the equation that we know in the past. So usually people do experiments to figure out what would be the true stress value at those corners. And they are usually greater than the reference stress. So we will pick up the highest stress value of the geometry and use the highest value to divide by the reference stress in order to get this K value. So what does K actually mean? K means for geometry under a certain load, how much you will get K times of your stress, of your regular stress, when there's an effect of stress concentration. So let's take a look at these three standard table. Over here you see a shaft with two segments. One segment has a larger diameter, the other one has a smaller one. So if you use the general equation to compute the normal stress, basically sigma equals to mc over pi d cubed. Even though let me show you. So sigma equals to C basically is like an R, and pi d. D is like a two times your R and cube, right? So in fact, if you are trying to compute the stress, for example, if there's this, I should use this example, bending. If there's bending, then this is what happened, right? For this case, the stress will be P over the area, so basically pi r squared. Okay, so no matter which situation, for the third one, stress equals to you can directly use 16T. I can directly use 32. Sorry, that was wrong. 32n over pi d cubed. This is right. And this is 16T pi d cubed. Okay, so no matter in which situation, either it's tensile, bending, or twisting, when we are studying at the position with larger diameter, we have lower stress. But when we are studying at the area with smaller diameter, we have greater stress. So in all three cases, the narrower area has greater stress. However, due to the geometry, at the corner, the fillet position, the stress is gonna be even higher. So in this particular case, the greatest stress was originally at this position where we have smaller diameter, but the stress at the corner is gonna be K times of the stress right here. How do you compute K? This table tells you. If you have a ratio of the radius of the fillet over the smaller diameter, so small r over small d, if you have this, and when this is going lower, if this is lower, that means you have smaller rounds, smaller fillets, then K value increases. So if you have a geometry that was made, if you have a geometry and you have a large fillet, large radius right here, K is lower. But if you have a very small one, K is higher. So if you have a small radius right here, K is higher. That means if you have stress here, the stress over here is gonna be K times of the stress, the reference stress. And it could be as high as 2 point, even double. It could be 2.5 times than your regular stress. Okay? So later on I will let you know, not only this, the stress concentration factor will affect fatigue, but also it will affect static load. Okay? So, which factor will also increase stress concentration? The other factor is this ratio, large capital D over small d. So if the ratio between two diameters are greater, here's the curve with 2. Here's another one with a lower one. So if this ratio is greater, then it concentrates, the stress concentrates more. Okay? So if you have a shaft design, you need to have diameter change in different area. Do not make a sudden change of the diameter, because that's gonna cause stress concentration at the corner. So if the shaft is gonna break, those corners could break more easily, because the stress over there are actually greater. Okay? Now, similar situation happened in all low conditions. How did they get those curves? Definitely by experiments. Usually a mechanical design book works with the manufacturer. So the manufacturer must have, or the researcher must have done a ton of experiments. They figure out how much more times of stress that is needed to break this. So they realize what is the concentrated stress. I should say, they figure out how much times stresses that was seen or measured at those corners. Okay. So now you understand the fact where we may have stress concentration. And we realize we have two kinds of symbols. Something is called KT, the other one is called KTS. So T represent T represent static. So S represents shear. So when you see KT, T represent the stress concentration factor for static loading. And if you don't see S, usually it's for normal stress. When you see S, it's for shearing. So this one is KTS, in fact. These two, they are just normal stresses, so KT. Now, how do we compute the ones for dynamic loading? Here. So there's two more tables. So stress concentration is actually affected by something called notch sensitivity. So what does it mean? So for different materials, like steel or aluminum, they behave differently when you have static load or dynamic loads. So Q is a factor that describes how the material behaves when it's carrying static load or dynamic loads. if you have Q equals to 1, then whatever KT you have, your KF is the same. What is KF? KF is the static concentration factor for dynamic loading. So if Q equals to 1, these two K values are the same. Do we want Q to be 1 or smaller? Smaller the better. Because if you have lower Q, that means your stress concentration factor for dynamic load would be lower than the static one. So it concentrates less. Okay? So let's take a look at what would be the factor that makes your Q factor greater. So if you take a look, focus on the steel. This is the table for Q. This is the table for QS. So QS is the factor, the notch sensitivity for shearing shearing stress concentration factors. And the Q1 is for the ratio between static K and dynamic K. So they behave slightly different. Now let's just focus on one figure. This is the notch sensitivity for static loading. Normal loading, normal stress. But talking about the relationship between static and dynamic. So for steel, if you have harder materials, then you have Q close to 1. So for harder materials, the stress concentration effect is very close to the one when it's under static load. Okay? However, if you have softer ones, this is a ultimate tensile strength. If you have softer material, then the dynamic stress concentration factor will be lower. Okay, so what will be the situation when you have greater Q? When the geometry, the special geometry, the radius of the geometry is greater, then Q is greater. So unlike the other effect in the past, Q lower is better. Because when Q is lower, KF is lower. So when KF is lower, we can have, if Q is 0, if in the extreme case Q is 0, that means KF is 1. When KF is 1, that means it doesn't concentrate. The stress is the same as the reference stress. That's better. That's great. However, in the diagram, you usually see it doesn't truly goes to 0. It's close to 0, but it doesn't truly goes to 0. Okay? So when you have larger geometry like this, under the static load, it will be having a lower K. But under the dynamic load, it will have a different effect. Okay? So, how do we put all these together? This is already mentioned. I use this table to help you to memorize the difference. So usually we have tables that help us to figure out what's the stress concentration factor for static loading. Sometimes we have normal stresses, sometimes we have shearing stresses. So you need to figure out which table to check. And later on, we need to check the other table, the notch sensitivity table, to figure out the Q. So using the Q equation, we can compute the stress concentration for dynamic loading. Same for shearing cases. So we actually have 4 different Ks. And how do we apply them to our design equation? So here's the where you can apply it. Because when we talk about dynamic loading, we have mean values and we have this is not yet, this is only static. So when we have static loads, go back to here, we have KT for normal stress, KTS for shear stress. So in fact, when you are studying your Mohr circle, you do see K greater stress concentration factors everywhere. So in fact, when you try to compute the principal stress, and you have sigma and tau, and if at that particular position you do see there should be stress concentration, then you need to multiply K. And you need to figure out what kind of load it's carrying, and you need to estimate what will be the K. And like I said, it's not the exact equation. It's a data, it's curve determined from experiments. So it's only a kind of estimation. But without this estimation, you will have a lower estimated stress. So in fact, in reality, when you have those notches, the stresses are greater. If you forget to consider stress concentration, you may see greater value. Okay, so stress concentration factors is one thing to help you to update your model and make it closer to reality. Okay, so for static ones, this is how you can apply your stress concentration factor. Stress, sigma is a normal stress, so you multiply KT. Tau is shearing stress, so you multiply KTS. So you can actually get those values from the table I just showed you, like right here. You just figure out what kind of problem you're dealing with. If we are dealing with the bending problem that we usually we have done several times, then you are checking the second table. But if it's also having twist and you need to see how much shear you have, then for the shearing part, you are actually checking the third table. Okay. So that's how you implement stress concentration in the static model. Here comes the troublesome part. How about for fatigue model? So this slide show you everything. Give me just 1 minute. Earlier we already separate the mean value part. We already separate the von Mises stress into mean value part and amplitude part. The mean value part doesn't change with time. The amplitude part changes with time. So we believe for all the mean stresses, we treat them like the static ones. So the stress concentration factor, we can use the static K. Same here, this is the mean of the shear, so we can use the static K, but for the shear one. However, for the amplitude, amplitude represents dynamic part of the stress. So for sigma amplitude, we use the dynamic K. This is the dynamic load and normal load. This is the one dynamic load and shearing. So here's where we can apply KF and KFS. How do we get KF and KFS? Use the Q and QS. So this is how everything becomes so messy. And this is the last slide. Okay? Based on our schedule, I still have time to show you more. I think next week, or let me check the schedule. I'm sorry to occupy a little more time. I just want to double check with you guys. Today I kind of speed up a little bit. Today is the 4th, right? I covered a lot for the fatigue. And next week we have the second exam. It's purely about static load. Don't worry about fatigue. Don't worry about stress concentration. So let me write it down here. Basically MSS, MSE, and MDE for static loading without stress concentration. Okay, so for the exam, only those 3 models. So next week we have exam on the 17th. We still have time for more fatigue model. So I will review what I did today, and then I know for this part we do need a lot of exercise because the equation is so long, and I know it's very confusing. So I will spend some time to show you how those equations can be utilized. So for the exam 3, we will have basically yield line, Goodman, Soderberg, with stress concentration. So in the 3rd exam, it's gonna be more complex because there's stress concentration in the 3rd exam. Okay, so that's everything I want to say. Maybe you need 2 hours for this one. If we will see. Okay. That's it for today. I will give you some time to check the attendance. This one, right? If you have questions, you can come here.
昨天有跟我说12要请假的人是阿文知道吗？他每听到了。他今天没有请啊？今天没有请。他今天没有来。对。还有谁？好。他说他是出公差的，他是车队要去比赛，车专比赛，就是他请的那2天，我的一个期末报告，一个期末考。是的。对啊，他请的那2天
就当他好。
他请的那2天期末报告跟期末考，他请的4天有2天就是最后2节课， 这有2节课是考试跟报告，大家会
太棒了，明年见。